Now, you'll be glad to know today's lesson is a very, very short lesson. There's one thing that you have to be able to do in this chapter with your eyes closed, and that is to generate a Kc expression for any balanced chemical reaction. Now, if you're asking me what's Kc, well, Kc is the way we measure the position of equilibrium. It's what we call the equilibrium constant, okay? The K is for the equilibrium constant. The little c I'll show you in a few moments means concentration. But we'll speak more about that later on. But just before we go on to that, just a recap of what we did in yesterday's class. Just take a look at this question here, which comes from your textbook at the end of this chapter. When bromine, a red liquid, is added to water, the bromine reacts with the OH minus ions in the water, and the following equilibrium is established. So you'll notice that the bromine reacts with the OH minus ions in the water, red, and forms a dynamic equilibrium with bromide ions, bromine oxide, and water, all colorless. That's extremely important, okay? So therefore, if I'm able to move the position of equilibrium in this particular system, I should be able to change the color. I should be able to move from red to colorless. Now, how would I do that? Well, remember what I told you yesterday? There are three stresses: concentration, temperature, and pressure. Mind you, pressure, the only time we can use pressure as a stress is when all the reactants and products in the system are in the gaseous phase. That's clearly not the case here because they are dissolved in water, so they're in liquid phase. So pressure would not be a stress in this particular situation. Anyway, let's read on. All of the species on the right hand side are colorless. Grand. Predict the direction in which the equilibrium will be shifted. So Le Chatelier's principle, and again, remember what Le Chatelier's principle says, because it is a definition that you can be asked. When a system in dynamic equilibrium experiences a stress, it will alter the position of equilibrium to neutralize the stress or to counter the stress. So predict the direction in which the equilibrium will be shifted if some sodium hydroxide, NaOH, is added. Now, sometimes this confuses people because the first thing they look at, they say, well, hold on, if I'm adding sodium hydroxide, there doesn't appear to be sodium hydroxide present in the equation that they gave me. And that's correct. However, what we've got to remember is this, that when you put NaOH into water, we can fall back on the old Arrhenius definition of an acid and a base, which says that when sodium hydroxide goes into water, it forms two things, Na plus and OH minus. Now, the Na plus is not part of this particular system, so it'll have no effect whatsoever. But the other part of the dissociated molecule, the OH minus, is part of this particular system and therefore will have an effect. Now, by adding sodium hydroxide, what we are also doing is adding OH minus, and we're increasing the concentration of OH minus. And if you increase the concentration of OH minus, that is you putting the system under stress. So what will the system do? It'll move the position of equilibrium to get away from the OH minus. In other words, the position of equilibrium will move to the right. And what will happen is that the red colour will become paler and paler and paler, and it'll move towards colourless. That's all we've got to say. Okay, so predict which direction. The answer is towards the right hand side. And then it says in part B what we just predicted a moment ago. What colour change will be observed on adding the sodium hydroxide? Well, if I'm adding the sodium hydroxide dissociates into Na plus and OH minus. The Na plus is not part of my system, the OH minus is, which means I'm increasing the concentration of OH minus, meaning, again, as I said already, it'll push the equilibrium away from that because it'll try to decrease the OH, get it used up. It'll decrease the concentration of OH minus by moving to the right hand side, and therefore we'll notice that the red colour will become paler and paler and paler. And then it says, suggest a way of reversing the colour change. Now, if adding sodium hydroxide increases the concentration of OH minus, therefore we can say and conclude that a base increases the concentration of OH minus. Now, ask yourself a very simple question. What's the quickest way to undo the presence of a base? And the answer is add an acid. Exactly. So when you add an acid, what that will do is it'll undo the presence of the OH minus, and it'll bring the equilibrium back to the left hand side. So suggest a way of reversing the colour change. The answer is to try and undo the stress that you've just done. So you've added in a base. The base has been distressed because it carries in the OH minus. Therefore, we want to undo that. And the only way to undo the action of a base is to add an acid. So therefore, one suggestion would be simply add an acid. Something like HCl or any of those bench acids that we use in school. Okay, so that's just a question that maybe just takes you beyond the comfort zone of what you were doing in the previous questions, which we've just worked through a few moments ago. Now, for the next 20 minutes or so, I want to talk about Kc. Okay, and what is Kc? What is the equilibrium constant? Now, the first thing I want you to notice is this. It's a constant, therefore it's a number. And it's a number that represents the position of equilibrium. Okay, so it's a number that represents the position of equilibrium in any system in which we have a reversible reaction. Keep that in mind, all right? And what we call it is Kc. So how do we know when a system has reached equilibrium? The answer is we measure its equilibrium constant. The first thing people could say is, well, you know, we know when a system has reached equilibrium because there's no further decrease in the reactant concentration and there's no further increase in the product concentration, so they must be occurring at the same time. That's true, but can we measure that position? And the answer is yes, and quite easily too, mathematically, but easily, as long as we have a balanced equation. We need to calculate Kc. All we have to be given is the concentrations of all reactants and products in the equilibrium mixture. Now, we can be given them in numerical form, or we can simply be given them in terms of the balanced equation. The balanced equation will give me the Kc expression, and then later on, when we come on to the more tricky part of the aspect, the mathematical aspect, we'll actually deal with given concentrations themselves. But if I want to get Kc, I have to be able to calculate what the concentrations are at equilibrium and show that there's no further decrease in the reactants or increase in the products. All the concentrations of products and reactants must be given in moles per litre. Okay, now moles per litre in chemistry is always like that, square brackets. So when you see that X, for example, that means X moles per litre. Square brackets always mean concentration. And we're going to be using square brackets when we don't know the numerical value of the actual concentration. We'll simply put the species in square brackets to say that we're dealing with the concentration of this particular substance at equilibrium. Okay. When a system becomes equilibriized, or if you want to put it that way, when a system comes to equilibrium, it has been found that a simple mathematical relationship exists between all reactants and products in that system. So when we reach equilibrium, again, a simple mathematical ratio. That brings us all the way back to the very start of fifth year, when we spoke about the fact that Dalton said atoms, as he taught at the time, all combine in simple whole number ratios. Lussac said what? That gases combine in simple whole number ratios. So therefore there's a pattern in chemistry, and the pattern in chemistry always is a simple whole number ratio. And in this case here, it's a simple mathematical ratio that exists between all products and reactants in that system. The reaction that we deal with has a specific Kc value, a specific constant, all right? And every reaction has its own particular constant that we can calculate from the reaction. The relationship is a constant value for a given reaction, and it's simply called Kc. Now, what does Kc mean? C reminds us that we're dealing with concentration. So in other words, we're going to be calculating the equilibrium constant by taking in the concentrations of all reactants and products, and K is the equilibrium constant. So K is the equilibrium constant, and C is the equilibrium constant being calculated using the concentrations of all reactants and products. So let's take an example. A moles of A react with B moles of B, and they set up a dynamic equilibrium with C moles of C and D moles of D. Now what do? We throw A and B into the system and we allow the whole thing to come to equilibrium. All right. And once we understand it's reached equilibrium, the way in which we calculate it is as follows. Kc for this reaction will be always the products over the reactants. Okay, always that way. So we start off with the concentration of C and we raise it to its coefficient. Then we multiply that by the concentration of D and raise it to its coefficient. We then divide that product by the concentration of A, which has been raised to its coefficient, multiplied by the concentration of species B, raised to the power of its coefficient. So therefore, you take the species and raise it to its coefficient. B to the power of B, C to the power of C, and D to the power of D. And these two always go on top. These two always go to the bottom. So what in essence you're forming is a fraction. Okay, so Kc will always be fractional. Now the fraction might break down into a whole number, but it'll always be a fraction initially when you're building the Kc expression. Okay, so let me just get rid of that there. And let's just put it in properly. So by experiment it has been found that Kc is equal to, here it is again, the concentration of C raised to the power of C multiplied by the concentration of D raised to the power of D over the concentration of B raised to the power of B and the concentration of A raised to the power of A. Do you notice the square brackets? Square brackets, concentration of C raised to its coefficient multiplied by the concentration of D raised to its coefficient divided by the concentration of A raised to its coefficient and the concentration of B raised to its coefficient. And you simply follow that for every single reaction that they give you. No matter what they give you, the Kc expression is something that can be easily written. Okay, and the square brackets, as we said already, means that the concentration of A, B, C and D are in moles per litre. And if they're not in moles per litre in the question, you have to put them into moles per litre before you can use them in this expression. Okay, so in order to write out the Kc expression, all you need is the balanced equation. So let's take an example here. Write out the Kc expression for the following reaction. Now again, when you're reading a chemical reaction, well, you read it chemically. So what does this mean? 3 moles of H2 plus 1 mole of N2 sets up a dynamic equilibrium with 2 moles of ammonia. Now, what's Kc? Kc for this reaction is a fraction. The top of the fraction always takes the product. So it's the concentration of NH3 raised to the power of 2 over the concentration of H2 raised to the power of 3 multiplied by N2 raised to the power of, oh, what? Well, don't forget the invisible coefficient. The only invisible coefficient we have is 1. So N2 raised to the power of 1. Now you don't need to put the 1 in, because as long as the species is there and there's no other number in that power position, then we know it's going to be 1. But if you want it, you can. It's no harm. Finished. That's it. That's Kc. That's how easy it is. But starting at the product, you put the concentration of the product to the power of its coefficient over the concentration of the reactants raised to the power of their coefficients. Let's just do one more. Okay, there it is there. If you want to see it written underneath, there it is. So it's H2 to the power of 3. Sorry, that's wrong. Shouldn't have put that up at all. That's the wrong way around. Go back, Divlia. Yeah, okay. So that should be, as I said already, do it again. It's NH3 to the power of 2 over H2 to the power of 3 and then N2 to the power of 1. So just do it again. Kc is the concentration of NH3 to the power of 2, so that's that taken care of, over the concentration of H2 to the power of 3 multiplied by N2 to the power of 1. And that's it. So you always start at the product end for the top of the fraction, and then you put the reactants at the bottom of that particular fraction. Okay. One more. Write out the Kc expression for the following reaction. 2 moles of CO, carbon monoxide, plus 1 mole of oxygen gas sets up a dynamic equilibrium with 2 moles of CO2. Now, what's Kc? Kc is a fraction. On the top of the fraction, you put in the concentration of carbon dioxide raised to the power of its coefficient, 2. Then on the bottom of the fraction, you put in the concentration of both reactants raised to the power of their coefficients. And finally, O2, which is raised to the power of 1. And that's your Kc expression. Okay, so they are that easy to write out. However, it is absolutely vital, before we go into the mathematical aspect of this thing, that you folks know how to write out Kc expressions. So I'm going to leave you with a few to do now. I want you to work your way through these, take your way through A, B, C and D, and work out Kc for each of those expressions. And again, I'll give you the solutions of these things at the start of class tomorrow.